Hey physics fans, and welcome to your Introduction to Rotation. Today we're going to be going over some rotational variables and some rotational kinematics. So let's get right in. Before we can understand how objects move when they're rotating, we have to understand the variables associated with rotational motion. So first, if an object is going around some circular path, then it goes through an arc length on that circular path. And the arc length is shown as our variable s. Now, while it's going through that circular path, it has some radius of curvature of that circular path, which is shown as our variable r. And the ratio between our arc length and that radius of curvature gives us the angular displacement shown as theta. The units for our angular displacement are in radians, which is, once again, the ratio between our arc length and our radius of curvature. Now, like translational motion, in rotational motion, to get the velocity of an object, we have to take the derivative of its position with respect to time. So the derivative of our angular displacement with respect to time gives us our angular velocity, which is shown as omega, and it's the relationship between the tangential speed and the radius of curvature of our path. Now, for our angular acceleration, we take a second derivative of our angular displacement to get the relationship between our angular acceleration and our tangential acceleration divided by the radius. Now let's look at the directions of these. To get the direction of our angular velocity, let's say that we're moving around our curved path S like so. So we're moving in that direction. So if we trace our fingers in the direction that we're moving, our thumb points in the direction of the angular velocity, which is coming out of the screen. Now, if the object is speeding up, then the angular acceleration will go in the same direction out of the screen as the angular velocity. If the object is slowing down, then the angular acceleration will go opposite or into the screen, so opposite of the angular velocity. Now, starting with our angular acceleration, we can integrate this to figure out our first rotational kinematics equation. So, if we integrate the acceleration from some initial to final time, we can figure out our first kinematics equation, which gives us the relationship between some initial and final angular velocity for an acceleration over time. Taking a second integral, we can get the relationship between some initial and final angular displacement given an initial angular velocity and our angular acceleration over time. Finally, if we solve the first equation for time and substitute it into the second equation, then we can get our third equation, which gives us a good relationship between an initial and final angular velocity for some acceleration over an angular displacement. That's it for today, physics fans. Make sure you review Chapter 10 if you have any questions, and see your instructor.